So we've just talked through this connection between angular velocity and linear velocity, and the sort of idea that if you know what the linear velocity of an object is and you know where the object is located, you can figure out what the angular velocity is. So if we consider this just an example of that, I've got some object that's moving at some velocity in this direction. If I want to figure out what the angular velocity is, really the question I'm asking is kind of what component of that velocity is in the direction that would result in changing theta, right? And given that component that's going to result in a changing theta, how big is that change in theta going to be, which is going to depend both on how fast the object is moving in that direction and how far away it is from the origin, which is why you've got this cross product here with r and v that picks up the part of the velocity that's perpendicular, and this divided by r squared accounts for the fact that the further something that was away from the origin, the faster it needs to be moving in order to result in the same angular change. Now, you might ask the question, well, if I can figure out what omega is from the velocity, could I figure out what the velocity is from omega? And if you reflect on that question a little bit, you'll pretty quickly convince yourself that you actually cannot do this. Okay, and the reason you can't do that is that, in fact, let's think about a sort of simple case. Let's imagine I've got some object that's moving directly away from the origin, right? If it's moving directly away from the origin, pretty clearly omega is not changing at all, but it has a velocity. So, and furthermore, that velocity could be whatever it wanted to be, and still omega wouldn't be changing at all. So although you can figure out what the angular velocity is from the linear velocity, you can't actually figure out what the linear velocity is from the angular velocity in the general case. You can, on the other hand, figure out what the linear velocity is from the angular velocity in the case where you've got some object that is just rotating. So if we just talk about pure rotation, so if I've got some point on that object that's located a radius r away from the origin, or a distance r away from the origin, and let's say it's rotating, so its angular velocity is omega coming out of the page, right? If I think about what the velocity of that is, well, the velocity, since it's pure rotation, right, my velocity is r dot r hat plus r theta dot theta hat in polar coordinates. Since it's pure rotation, the distance from the origin is not changing, so this term is 0. So if I know what my angular velocity is, I can figure out what my linear velocity is, and it's actually fairly easy to convince yourself that from a cross product perspective, you could calculate what that linear velocity was by saying that the linear velocity was omega cross r. Let's take a minute to see if that actually makes sense. So here I've got omega coming out of the page. I've got r is pointing up. So omega crossed into r is going to give me a cross product that is in that direction, right? K hat cross j hat gives me negative I hat. So my velocity would be like that at that point. That makes sense. Similarly, if my object were here, r were in that direction, omega crossed into r would give me a velocity down. If r were here, omega crossed into r would give me a velocity to the right, and so on. So for pure rotation, I can figure out what my velocity vector is based on what the location of the object is and what my angular velocity is. Now that might seem like it's a limiting case, but let me propose a sort of big idea that you want to use this for. You can think about taking any motion of an object, of a rigid body, and decomposing it into two parts. The motion of the center of mass plus the motion about the center of mass. In other words, the first part has to do with how the center of mass is translating, and the second part has to do with how the object is rotating about the center of mass. So let me give you an example of that, and let's see how that then plays out mathematically. So one sort of example of that is, let's imagine I've got a frisbee. So here's a coordinate system, and let's say the frisbee is here in the xy plane, and it's spinning, right? And so about the center of mass, if I take the origin as being the center of mass, I would say the angular velocity of the frisbee about that origin, right, would simply be whatever my value of theta dot is in the k hat direction, right? So this is omega of the object about the center of mass. If I'm interested in some bug that's sitting at a point on that frisbee, I could figure out what the velocity of that bug was by saying, you know what, actually the velocity of that bug in this coordinate system about this origin is, well, the position is this position, our center of mass, plus this position vector, which is the position vector of the bug with respect to the center of mass, right? So in general, the position of some point on the object, so bar of the bug, right, is equal to the position of the center of mass plus the position of the bug with respect to the center of mass. Okay? Now if I ask the question, what's the velocity of the bug? Well, the velocity of the bug is the time rate of change of the bug's position. And since the derivative is an operator that distributes here, that is going to be what the velocity of the center of mass is, right? The time derivative of this first term, plus the velocity of the bug with respect to the center of mass. But with respect to the center of mass, the only motion is rotation. So that second term, right, just has to do with the fact that the frisbee is rotating. So that second term is simply going to be omega cross with the position vector of the bug with respect to the center of mass. So there's sort of an important idea here that you can break motion down. When you've got some object that's both rotating and translating, you can break that motion down into center mass motion plus rotational motion. That idea ends up being quite handy for both figuring out what equations of motion are, but also for understanding how motion actually happens. And in the next video, we'll talk about how rolling motion looks and think about this idea with respect to rolling motion.